So we want to talk about Chapter 10 using OpenStax, and we want to discuss liquids and solids. In particular, we're going to start here with intermolecular forces. Now, inter means between. Molecular is molecules. And forces, these are going to be forces of attraction or forces of repulsion. We're going to be looking at electrostatic forces pushing things apart or pulling them together. So, intra versus intermolecular. An intramolecular force is a very strong force, and our intra is either a covalent or frequently an ionic bond. And these are going to have energies of hundreds of kilojoules. These are very strong to break, and this is not what we're discussing when we're talking about this chapter in liquids and solids. We want to talk about what holds two molecules together. Now, what holds two molecules together is a weak force that is in between them, and we're going to call these intermolecular forces. If we want to go between a gas, a liquid, and a solid, and we know what these are. We know that gases have a lot of kinetic energy. So if we're looking at our kinetic energy up here, these guys have a high kinetic energy, and these guys are going to be not stuck together. They're going to have weak interactions, meaning whatever forces we have in them are going to be so weak that they pretty much ignore each other. Now, if we go to a liquid, to go from a liquid here or a gas into a liquid, we know that here our temperature is going up, and here going in this direction, our temperature would be going down. As we decrease our temperature, we're going to go from a gas to a liquid to a solid. The difference between a gas and a liquid is that these guys have noticeable intermolecular forces. These guys are stuck together. And we know this because they're going to take the shape of any container you put them in. Gases are going to expand to fill any container. Now, a solid, solids are going to have two options. They're either going to be cold or they're going to be well stuck together. Well stuck together means that they are going to have large intermolecular forces. We're going to shorthand those from now on as IMFs. And if they have strong intermolecular forces and they're well stuck together, they're going to be a solid. If they have weaker intermolecular forces at some given temperature, they're going to be a liquid. And if they have very weak intermolecular forces at a given temperature, they're going to be a gas. If we take butane, butane is a nice organic compound that we use because, like most of them, it undergoes combustion, which means it burns nicely. And if we take and we put it into a sealed container and we have a high pressure on it, we can take a gas, which is what butane is at room temperature, and force it to liquefy. We can take and put a high enough pressure on our gases to force a gas to become a liquid, force the intermolecular forces to take over. So, intermolecular forces, these are also called van der Waals forces. And we have a number of different kinds. And we have dipole-dipole and a very specific case of dipole-dipole called hydrogen bonding. And we need to be very careful when we do hydrogen bonding to realize that this is not a bond. When we talk bonding in chemistry, we're talking ionic and covalent. This is not a bond. This is a very weak intermolecular force. We're also going to have a London dispersion forces, and those are also going to be called here dispersion forces, and these are going to be our options. We're going to have dipole-dipole, hydrogen bonding, and we're going to have London dispersion forces. Now, when we talk about polar molecules, and when we talk about polar molecules, we need to think about back from Chem 111, and we need to think about things like water. And we know that water has two lone pairs, two hydrogens, and with its nice two lone pairs and two hydrogens, we know that the top here doesn't look like the bottom, and this molecule is polar. And we remember that polar means it's going to have a negative end and a positive end, because polar means it is an electric dipole. And by electric, we mean positive on one end and negative on the other. So if we have polar molecules, for example, water, they are going to undergo or have dipole interactions, or they're going to be held together by intermolecular forces, and our intermolecular forces we're going to call dipole-dipole interactions. Why? Because the molecule is polar. So, dipole-dipole. This is when one polar molecule encounters another polar molecule. The positive end of one of them is attracted to the negative end of another. So if we go back to that HCl case that we had before, we know that HCl looks like this. This end is partial positive. This end is partial negative. Remember this being partial, which simply means a little. As we got a partial positive and partial negative, it means that this end is essentially positive and this end is essentially negative. Now we're not talking ionic, we're talking just a little bit, such that this thing is still a molecule. When we put another HCl here, the positive end of the other HCl, which is going to be this one right here, is going to stick to the negative end of this one. So we're going to have an interaction, and this is going to be our dipole-dipole. This is simply when two polar molecules are going to be attracted. This is like an ionic bond, but it is much, much weaker. Why is it much weaker? Because we're not a full positive and negative like Na plus and Cl minus. We're talking partials. Partial means just a little. So it's nowhere near as strong because it's just a little bit positive and negative. Now we're going to find that this is going to explain properties like boiling points of a lot of polar compounds. So polar molecules. Our polar molecules are going to have a partial positive and a partial negative end, and then they are simply going to stick or interact with the partial positive, the partial negative end of another molecule. So if we had something like formaldehyde, which looks like this, we know that this end has lower electronegativities, making it partial positive. This end with the oxygen has a higher electronegativity. And if I stick, making that partial negative, if I stick another formaldehyde in here, we're going to have an interaction. And this interaction is going to be the negative end of one with the positive of the other. And this is my dipole. We shorthand dipole as a D interaction between two polar molecules. Now, we have a very interesting specific case, and our interesting specific case is hydrogen bonding. Hydrogen bonding is a really strong intermolecular force, strong for an intermolecular force at least, and it's a specific case of dipole. So the first thing we're going to have is a molecule that's polar. The next thing that we're going to have is a hydrogen on this molecule bounded to a very, very small, highly electronegative atom. And our examples and the only ones we can have are nitrogen, oxygen, and fluorine. So we're going to call this NOF, and we have to have a hydrogen that's attached to one of these. And if we have that, we are going to have hydrogen bonding. Now, this is going to give us our partial negative end, and this is going to give us our partial positive end. A case on this could be ammonia. Now again, to have any sort of intermolecular forces, you have to have two molecules. If we're going to have hydrogen bonding, we have to have a molecule that has, again, the NOF, a nitrogen attached to a hydrogen, or oxygen attached to a hydrogen, or fluorine attached to a hydrogen. And then we have to have another one. So we'll put another one over here. And if we put another ammonia over here with its lone pairs, these are going to interact. Now I know you're going to say that's just the same as we had before, where this is partial negative and this is partial positive, and this is pretty much a dipole-dipole interaction. And I agree with you, it is, except this is a specific case. And this is our hydrogen bond. It's a little stronger, actually it's a fair bit stronger than straight dipole-dipole interactions, and it occurs for two reasons. One, nitrogen, oxygen, and fluorine have a very high electronegativity, and the other thing that they have is that they are very small, which means that the distance in between here, this distance, is very small. And this partial positive and partial negative are as large as they can get. So this partial positive and negative is large as possible over a space that is as small as possible. So it's going to be a large difference over a small space. And when we have this large distance over a small space, we get a very special interaction. So where could we see this? Well, first of all, this is water, and this right here is the hydrogen bond. And again, we're looking for NOF and H, meaning we have to have a hydrogen attached to an oxygen. And once we do that, it has got to find itself and interact with another, in this case, hydrogen or an oxygen, etc. So notice oxygen here attached to a hydrogen interacting with another oxygen. This interaction is a hydrogen bond, a strong case of dipole-dipole interaction. What does this mean? Well, if we take a look at some cases here, and I'm going to do the top row in blue, where we have H2S, we have H2SE, and we have H2TE. And we're looking at boiling points. And notice these guys are getting heavier, and our boiling points are going up. That makes reasonably good sense. The heavier it is, there should be some effect of trying to pull these guys apart as they get larger and heavier, and that is pretty much reasonable. But what about these guys? Notice this is group 6, and this is H2S. Now, the element that we're missing here and the molecule we're missing here is H2O. These guys are polar. H2S, H2SE, and H2TE are all polar, which means that they have dipole-dipole interactions. But if we put water under here, it's not going to have straight dipole-dipole. It's going to have a hydrogen bond. And we know that a hydrogen bond is stronger, so it should have some effect. And it really does. Because when we put our water in here, our boiling point goes from minus 60 degrees centigrade for H2S to 100 degrees centigrade for H2O. Now this is boiling, meaning this is the process of going from a liquid into a gas, which means we are pulling the molecules apart. As we pull these molecules apart, we're going to have to add a lot more energy because here, when we go from our H2O to our H2S, this is much more strongly stuck together. H2O, hydrogen bond, and we can see how strong this effect is by looking at our boiling point. We also see this with HF and ammonia. Now, if we had taken and we put in here compounds of carbon or of group 4, which are nonpolar, it's straight down. All right, we only see this when we have our nice NOF, our NOF, nitrogen, hydrogen, fluorine, nitrogen, oxygen, and fluorine attached to a hydrogen, giving us hydrogen bonding. We also see this in our DNA bases. Our DNA molecules are held together by hydrogen bonding. Hydrogen bonding is actually strong enough that we can see it with dynamic or atomic force microscopy. Now, this is a molecule that I know you don't care about, but nonetheless, this is naphthalene tetracarboxylic diimide. The point being, these right in here are covalent bonds. And the hydrogen bonds we see in this picture here, but we see them right here. The hydrogen bonds are actually strong enough if we do spectroscopy that allows us to actually see the molecule, we can see these little blurry outlines of weaker, still measurable hydrogen bonding. So that takes care of the basics. That takes care of polar molecules. Polar molecules have two options. Polar molecules are either going to be held together by dipole-dipole, or if we are not, we're going to have a hydrogen. But what if it is nonpolar? Well, nonpolar is more complicated because nonpolar inherently has no positive and negative end, and it shouldn't stick. In order for molecules to stick, there has to be some attraction. We have to have some partial positive and partial negative causing them to come together, but nonpolar doesn't have that. So what's going to hold them together? Because we know they are held together, because we know we can even take things like helium and we can turn this into a liquid. This is about as nonpolar as we can get. But if we can turn it into a liquid, it means it sticks. And if it sticks, it has to have some sort of partial positive, partial negative. Well, our discussion on this, or our name for this, is called dispersion forces. We also call them London forces, and sometimes even London dispersion forces. Now note, what has London dispersion forces? Everything. Everything has dispersion forces. As long as it's got electrons, it's got dispersion forces. So, dispersion forces. So I want to imagine, and you're just going to have to forgive my drawing, that we have helium. Now we know that helium has got its protons, it's got its neutrons, and someplace out here it is going to have some electrons. All right. So if we put another helium in here with its protons and its neutrons and its electrons. All right. So we'll draw our little atoms here. And then we look at this and think there's no reason for these to stick. But if we imagine, what happens is what sort of looks like it's happening here is that the electrons from one of the heliums are just a little shifted to one side of the atom or another on its own, simply because electrons are moving. The other electrons from another atom can interact. So what does this mean? This means we have a tiny, and when I say tiny, I mean tiny, that's small, tiny partial positive and partial negative. This is a temporary dipole. Now note, something that's very polar can actually do this to a molecule or an atom, but they can also do it on their own. And this helium is doing it on its own. It is taking, and by having the electrons on one side, so the electrons are over here, and the nucleus is over here, it's going to have a temporary dipole. It's going to be partial negative here and partial positive. What happens then is that these electrons see this nucleus, and as soon as they do that, they're going to make a partial negative and partial positive over here, and your dipole is tiny and temporary. Well, if our dipole is tiny and temporary, these guys can stick. How much? A little tiny bit. And so what we're going to have here is an uneven distribution of electrons. And you can see this for two nonpolar diatomics, for example. So if we had fluorine, we could make fluorine stick together. Why? Because one fluorine atom is going to be bonded to another. They're going to have its electrons. But if the electrons here can get pulled by the nucleus on this fluorine, it can take and make this end partial negative, interacting with a partial positive here, and giving us an uneven distribution, and we're going to have a temporary dipole. This is our explanation on what occurs. Now we know this occurs because we can make these guys stick. For example, if we have chlorine, bromine, or iodine at room temperature, chlorine is a gas, bromine is mostly a liquid, and iodine is a solid. So, gas, liquid, and solid. First of all, iodine is nonpolar. So why would a nonpolar molecule be a solid at room temperature? And the answer is because it has large dispersion forces. Now, why does it have large dispersion forces? It has large dispersion forces because it has a large polarizability. What does polarizability mean? Polarizability means that the electrons are loose. They're free to move. And they are loose because the radius of the atom or the molecule is large. The electrons are a long way from the nucleus. And when they're a long way from the nucleus, they are easy to move. And if they're easy to move, then they'd be shoved over. And when they can do that, they can give me a nice partial negative and partial positive, and this temporary dipole becomes larger. So what are we going to do with this? Well, we're going to realize that as the radius of a molecule goes up, the polarizability goes up, and the dispersion forces go up. Now, radius can be hard to keep track of, so we're going to do it a different way. And instead of doing radius, we're going to do molar mass. And we're going to say that as the molar mass goes up, the polarizability goes up, and the dispersion forces also are going to go up.